Okay, now we want to find out what are the other states in this, in this ladder. Okay, we want to find out other states in this ladder. Okay. The other states in this ladder. This ladder has another name coming from group theory. It's called a multiplet. Okay, and multiplet is usually it's a vector space, a finite dimensional vector space on which some Lie algebra or some algebra acts on. Okay, so we will use the word multiplet a lot. So multiplet is nothing but a finite dimensional Hilbert space. Okay. Okay, so how do we find, say, j minus 1? Any ideas? We found jj is equal to j1 times j2. This we have found already.
Lowering operator.
Right. So we are going to apply the j minus operator on j. Okay. So let's do this. So j minus acting on jj is going to be equal to j1 minus acting on, now okay, on j1, and then we have j2, and then we will have j1 with j2 minus acting on j2. Does this make sense? Also, it probably answers Nahi's question.
Yes, sir.
Okay. So, I mean, just, I know even if you understand, let me just like break this down a little bit. What I mean very explicitly is that j minus is an operator which consists of j1 minus cross the identity operator acting on the second Hilbert space plus the identity operator acting on the first Hilbert space cross j2 minus, so that when I apply j minus on j, this means that this thing is acting on j1 cross j2, and sorry for the mess. I'm just gonna copy and paste this thing. Okay, so this operator is acting on these guys, and so this operator consists of two terms. The first term, this thing will act on this, so j1 minus j1 cross this thing will act on this. This is just j2, and then plus this one will act on this guy, which is j1 cross this guy will act on this thing, so j2 minus j2. Okay, and that's what I've written here. Okay, are there any questions?
No, sir.
Okay, so let's carry on. So now we use those nice formulas that we derived when we were doing angular momentum, and let's look at what the left-hand side is. The left-hand side is going to give me j minus acting on jj is equal to square root, inside it's j plus 1 minus j minus 1. Okay? And then times j minus 1, right? So if I simplify this, this is, the first term, this guy and this guy cancel. So I have square root of 2j multiplying j minus 1. So this is the left-hand side. What about the right-hand side? So the right-hand side is going to be, this term plus this term. The first term is just going to give me square root of j1 plus 1 minus j1 minus 1, and then j1 minus 1 times j2 plus j2 plus 1 minus j2 minus 1 times j1 times j2 minus 1. Do you see what I'm doing here? I mean, I'm applying the lowering operator to every term. And this is the, these are the factors, the proportionality constant that I'm getting. So of course, this can be written as 2j1 minus 1 j2 plus square root of 2j2 j1 j2 minus 1. Now if I take the left hand side and the right hand side together, now I get j minus 1, and that is just going to be given by square root of j1 by j times j1 minus 1 j2 plus square root of j2 by j j1 and then j2 minus 1. Okay, so this is the second state in our multiplet. Okay. All right, so from the first state, we derive the second state. So does that make sense?
So here j is j1 plus j2, like just as before.
Yeah. Here, in all of this, j is j1 plus j2. Right? But here you see the m value has decreased by 1. So the total m value is j1 plus j2 minus 1 for this guy. So that could be either by reducing the m value here or the m value here by 1. And these are the coefficients of linear combination, okay? So these linear combination coefficients, they are very important. They have a name. Sorry. They are called Klebsch, SCH, I think. SCH, Klebsch-Gordon coefficients, okay? Or Gordon. So this is not the same Gordon as Klein-Gordon. There's an A here, okay? Many physicists, even after teaching quantum mechanics all their lives, do not notice this. Okay, so these are called Klebsch-Gordon coefficients, okay? And they have an interpretation which I'll come to later. Okay, now, how do I find j minus 2?
We applied the lowering operator again.
Right, we do it again. Okay, so I'm not gonna bore you with that because pretty soon we'll do some examples. and you'll see, over there. But right now, I want to move on to another multiplet. So this is, by applying J minus enough times, we can generate all the states in the multiplet for which J is given by J1 plus J2. So that is going to be a vector space. But remember that we assumed that this is going to be the case of the highest value of J. And the classical picture, and there's a quantum mechanical analog, which means that the two angular momenta are essentially pointing in the same direction, right? But we know that they don't have to. And in quantum mechanics, they can point in directions which are quantized. So what are the other possibilities? Well, the next possibility is that J is going to be J1 plus J2 minus 1. So this is meaning that J is slightly, J1 and J2 are slightly, they are not exactly parallel. If they're completely anti-parallel, we are going to get J1 minus J2, and we're going to get that by going down one quanta of angular momentum at a time. Okay, so the next multiplet that we will look at will have the total angular momentum value of this. Okay, and you might say, why is this? Why not say, why didn't we take J equals to say J1 plus J2 minus square root of 2? Why isn't this possible, right? You can prove why this is the case, but a better thing to do is to actually construct all of the states explicitly and then sum them all to make sure that we haven't missed anything. Okay, and that's the approach we're taking. So we are assuming that every time we go down the total angular momentum, we go down by 1. Okay. Do you understand what I'm trying to do here? I'm trying to create a different Hilbert space where the maximal weight state is not going to be J1 plus J2, but it's going to be J1 plus J2 minus 1. So this will be our maximal weight state, okay? You can see that this is a different state than the previous maximal weight state. In the previous maximal weight state, we took J1, J2, and J1 plus J2, right? Here, this value has been reduced by 1, and therefore, the highest value that M can take will also be reduced by 1, right? This is do you understand what I'm doing?
Yes, sir.
Okay. Okay, so let's do that. So, now, because we know that Jz is J1z plus J2z. And because J is J1 plus J2 minus 1, this state, let's call it, okay. Let me not call this J, okay? Let me not call this J. Let's, let us, let us say J is always, the definition of J is always J1 plus J2. So what we are trying to do here, we are trying to find out the maximal weight state, which is going to be J1 minus 1, J1 minus 1, okay? It's just a change of notation. Do you understand what I'm doing?
Yes, sir. Yeah.
Okay. So here also, let me, yeah. Okay. So how can, now the thing is that, because Jz is J1z plus J2z, if this guy is going to have the value J minus 1, it can only happen if this has J, if this has J1 and this has J2 minus 1. Or the first one has J1 minus 1, the second one has J2, right? Because J is J1 plus J2. So the total Jz has to be J1 plus J2 minus 1. And it can happen in two ways. Either J1 can have J1 and J2 can have J2 minus Z, so J2Z. Or J1Z can have J1 minus 1 and J2Z can have J2. Is that clear?
Yes, sir.
Okay, Shujosh is clear about that. What about other people? Okay, I think Kali also is sure about this. But what about other people? Shall I go over this again?
Yes, sir.
Okay.
Keep going.
Yeah, sure. So, okay, so in the previous, above, what we have done is that we took J to be J1 plus J2. And this corresponded to the two, I'm drawing a inaccurate diagram, but is where J1 and J2, the two angular momenta are parallel. So, and then what we did is that we found all the states in that multiplet starting with the highest weight state, which was this thing. And we applied on it the lowering operator. But what was the highest weight state? This state was J1 times J2 J2. Now what we do is that we are taking a physical configuration where J1 and J2 are not exactly parallel. They might be a little bit out of alignment. So then we are going to say that, okay, in that case, the highest weight state will be now J minus 1, where J is given by this expression. So now the highest weight state is going to be J minus 1. This will be the J squared angular momentum quantum number, and this will be M value is J minus 1. Okay. So I'm going to treat that as a highest weight state.
So is the first term the J squared angular momentum number?
Well, the J squared value will be J minus 1, J minus 1 plus 1.
Yes, sir.
I'm just
Oh,
using shorthand. I'm not going to write the
okay.
whole. I'm not going to write this thing all the time. I'm just going to write this.
Yeah,
time,
okay.
right? I mean, there's something convention that we have established. Okay. But it comes from J squared, right?
Yes, sir.
Yeah. Okay. So this is what we're going to do. Now, this can happen in two ways. It can happen by, if I take J1, it can happen in, J1 minus 1, J2, J2. Remember that these components always have J1, J2. These are all fixed. And then it can also happen in another way, which is J1, J1 times J2, J2 minus 1, right? These are the only two ways that we can get this Z component, right? You take one from here or one from here. Does that make sense?
Yes, sir.
Yeah, because this is JZ, this is JZ1, this is JZ2, this is JZ1, JZ2. But you see that in the previous multiplet, there was already a state which was a linear combination of these two guys. This thing, remember? So this state cannot be the same linear combination as before, but it doesn't have to be. What we have to do is here we put J1, J, here we put J2 by J, but in the previous case, there was a plus sign between them. But if I put a minus sign, this is a different state, right?
Yes, sir.
So this is how we find the maximal weight state of a new multiplet, just by putting a minus sign here. Because we know that the plus sign is already included in a multiplet before. And then we want to find all the other state in this multiplet. What do we do?
Apply the lowering operator.
Yeah,
to
we
this
start
maximum.
applying lowering operator and automatically we get all the other states. Okay.